Mass spring system motion. A mass spring system consists of a mass attached to a spring, which is attached to a support. Illustrated is a horizontal mass spring system, where the spring is first compressed, squeezed in, or stretched in that direction, and it oscillates between the maximum compressed stretched point. Energy is constantly being transferred between kinetic energy and elastic potential energy. A cycle is a full to and fro motion where the mass returns to its starting point, same as one trip around the circle in UCM. So let's look at these pictures here. This box here was pushed in. It started at this little dashed line here. That's the equilibrium point. We'll get to that. You push it in and let it go. Well, it's going to move this way. Then it'll move all the way out to here. Then it'll start coming back. It'll cross the midpoint again here. And finally, it winds up here, back where it started. And then it just reverses its motion. The time it takes to complete one cycle is the period. Frequency is the number of cycles completed per second. Again, just like uniform circular motion. Displacement, x, is measured from the equilibrium point. Right there. That's where x is equal to 0. The spring is neither compressed nor stretched. Hooke's law states that the force at that equilibrium point is 0, right? Because F is equal to minus kx, x is 0, force is 0. Amplitude is the maximum displacement. So in this case, here's your equilibrium. If you were to pull the spring out to here, that distance a is the displacement. That corresponds to the radius in uniform circular motion. The period of a mass spring system is 2 seconds, and the amplitude of its motion is 0.40 meters. How far does the mass travel in 4 seconds? We've got the period, 2 seconds, amplitude is 0.40 meters, and the time is 4 seconds. So we'll sketch this one out. The spring will be stretched until the mass is at plus a at time equals 0, and then we'll let it go. In one period, that is t equals 2 seconds, the mass will travel to negative a and then come back and wind up at plus a again. It will cover a distance of 4 times a, or 4 times 0.40 meters, 1.6 meter, right? Because go from here to here, there's 0.4 meter, here to here, another 0.4 meter, then you come back, another 0.4, and another 0.4. So that's 4 of them. And that's why we multiplied a times 0.40. So in 4 seconds, the mass will oscillate for 2 periods. So what distance does it cover then? Well, in one period, it covered 1.6 meters. So in 2 periods, it's just 2 times 1.6, or 3.2 meters. What is the spring force in a spring with the spring constant of K equals 100 newtons per meter that is stretched by 10 centimeters? The givens are spring constant is 110 newtons per meter, and be very careful, convert x to meters, so 10 centimeters is 0.10 meter. We'll use Hooke's law, F is equal to minus kx, substitute in the givens, and we get a force of negative 10 newtons. The negative sign indicates that the force acts to move the mass back towards the equilibrium point. That's what's known as a restorative force. The minus sign in Hooke's law indicates that it's a restoring force. It is directed to restore the mass to its equilibrium position. K, of course, is the spring constant, and very, very important, the force is not constant as it depends on the position, so the acceleration is not constant either. The maximum force exerted on the mass is when the spring is most stretched or compressed, where x is equal to negative a or plus a. So F is equal to minus Ka. The minimum force exerted on the mass is when the spring is not stretched at all, where x is equal to 0, you're at the equilibrium point. In that case, the force is equal to 0. Now we'll go through some scenarios here. First, the spring is all the way compressed. Right, here's the equilibrium point. It was pushed or compressed all the way to the x equals minus a position. So the displacement is at the negative amplitude. The force of the spring is in the positive direction, right? Because x is negative, so F equals minus kx, that gives you a positive number. And that's shown here. The spring is pushing back. The acceleration is in the positive direction, and the velocity is 0. It momentarily stops at that side. The mass was let go, and the spring pushed it in this direction. Here's the equilibrium point. So at the equilibrium point, the displacement is 0. The force of the spring is 0, because F equals minus kx, x is 0. The acceleration at this point is 0. Why? Because the force is 0. And good old Newton's law, force is 0, no acceleration. The velocity is positive and is at a maximum. When the spring is all the way stretched, and that's at the x equals a position, right? It started at minus a, and it'll go to positive a. It momentarily stops and changes direction. So at that point, the velocity is 0. So when your displacement is at the positive amplitude, the force of the spring is in the negative direction. It's trying to pull it back. The acceleration is in the negative direction, right? Because whatever the sign on the force is, that's what the sign on the acceleration is. And the velocity is 0. When the spring is at equilibrium and heading in this direction, the negative direction, the displacement is 0, right? You're back to the equilibrium point. The force of the spring is 0. F is equal to minus kx. The acceleration is 0. And now your velocity is negative and at a maximum. So the velocity is always going to be a maximum at the equilibrium point. Because why? Well, the force was pulling it this way, continually accelerating it and making it go faster. But once it crosses the equilibrium point, the force switches direction. It's now slowing it down. So your maximum velocity is at equilibrium, regardless of which direction you approach it from. Now let's make a vertical mass spring system. The only change will be the equilibrium position, which is at the point where the spring force equals the gravitational force. Right, here's gravity. So if we just lower it down and do it very gently and then stop holding it, it will stay there. So gravity's pulling it down. Hooke's law, the spring force is trying to pull it up. So this displacement from the original position here, when there was no mass on it, is x0. So you have minus kx0 is equal to mg. And going forward, if I let it rest there and then pull the mass down, I measure all distances from this new distance here. So the effect of gravity is canceled out by changing to this new equilibrium position. Of course, gravity is still there. It's just being balanced by the spring force. A spring stretches 5 centimeters when a 1 kilogram mass is suspended from it. What is the spring constant? Okay, as always, we start with our given. Here's the mass. N converts centimeters to meters. First, draw a free body diagram showing that the spring force acts opposite the stretching force due to gravity. Write Newton's second law. So this really isn't a free body diagram. It's pretty close. You should have a little dot here that represents the box. So the box has stretched the spring by distance x. So we have the force of the spring in the up direction and mg down. And it's at rest. So we have Newton's second law, F equals ma. And our forces are F spring, which is in the up direction. We'll take that as positive. Mg is down direction, so that'll be negative. And since it's not moving, it's equal to 0. So the force of the spring is mg. And we'll continue on the next page. A spring stretches 5 centimeters when a 1 kilogram mass is suspended from it. What is the spring constant? Now we'll use Hooke's law, which is F spring is minus kx. We solve for k, and k is minus F spring over x. We substitute in our givens and what we found on the previous slide, that the force of the spring is mg, and the displacement is down, so we give that a negative sign. That's negative x. We substitute in our values, and we get k is 19.6 newtons per meter. And you might worry what happened to the negatives. Well, there's a negative down here, negative here, they just cancel out. So our spring constant, 19.6 newtons per meter.